a problem L is NP complete if, number one, L itself belongs to NP, and number two, for every problem L prime that belongs to NP, L prime is polynomially reducible to L. Okay? So, of course, we will not fully understand all of this stuff until we give some actual examples and some actual reductions. Okay. So what we are saying here is a problem is NP complete if the problem itself belongs to NP, which means that the problem is verifiable in polynomial time, and if every problem in NP is reducible to this problem. Any problem in NP can be reduced to this problem, which means that any problem in NP is less than or equal to this L in the level of difficulty. Or in other words, L is at least as hard as any other problem in NP. Okay? Now, well, this means that using this approach, in order to prove a problem to be NP complete, we will have to prove that every problem in NP is reducible to that problem, and that's hard. Well, that kind of proof had to be done for the very first problem that was proven to be NP complete. So that problem was formula satisfiability. Or let's call it SAT. What's formula satisfiability? You are given a logical expression, and you are asked to determine a logical expression like, x1 and not x2 or x3. So a logical expression that consists of ands and ors and logical variables or Boolean variables. Is there any assignment of these variables that will cause this to evaluate to true? Well, in fact, in this case, yes, there is. So if you set x3 to 1, it doesn't matter what you set x2 and xy to. Yeah, because if x3 is 1, then you can set xy and x2 to 0 or whatever, and you will get the whole expression will evaluate to 1. Right? Now, this is an example of a formula that is satisfiable. So you can find the assignments 0, 0, 1 will cause this formula to evaluate to 1. Now, can you give me a logical formula that is not satisfiable? There are no values of the variables that will cause it to evaluate to true. A formula that is never true.
x1 and x2 and negation of x2.
x1 and negation of x2? Well, I can set x1 to 1 and x2 to 0.
Negation of x1.
Yeah, x1 and negation of x1. This is a formula that is never satisfiable because it has a contradiction. Right? So this is satisfiable. This is unsatisfiable. Now, if I give you a formula that consists of n variables, so given a logical formula that has variables, or using variables x1, x2 through xn, determine if there is an assignment, we call it a satisfying assignment, an assignment of the variables that will make the formula evaluate to true. Okay? Now, in general, this problem does not have a polynomial time solution. Now, what's the brute force solution here? What's the brute force solution to this problem?
Try all the combinations.
Yeah, try all the combinations. And how many combinations do we have?
N.
So it's to the number of variables.
Yeah, 2 power n, because each variable has 2 possibilities, true or false, and we have n of them. So brute force is 2 of n. Brute force is omega of 2 power n. Is at least 2 power n, because the worst case running time of the brute force solution is at least 2 power n for the worst case. Of course, there is always a best case, right? You can get lucky, and the very first assignment that you try will evaluate to true. So remember, a best case is a lucky case. And here you can get lucky, and the very first assignment that you try will happen to be true, and you are done. But in fact, if there is no satisfying assignment, there is no way to prove that unless you go through all possible combinations. So this is a problem. This is another problem that is NP-complete. Now, this was the first problem to be proven NP-complete. So someone proved that any problem that belongs to NP can be reduced to this problem. If you are given any problem. So this must be very abstract proof. So proving that any problem in NP can be reduced to this problem. So this problem, if you solve this problem, then you can solve any problem in NP in polynomial time. Okay. Now that was how the first NP-complete problem was proven to be NP-complete. But now that we have some problems that have been proven to be NP-complete, we can use them to prove the NP-completeness of other problems. So think about this. The example that I like to present here is, if you are trying to identify the tallest people on campus. So we have 30,000 students on this campus, with faculty and staff and everything. And we're trying to identify the tallest people on campus. So we're trying to find those people that do not have anyone taller than them. So they all tie. They are all of the same height. They are taller than anyone else on campus. Now, this is the club of the tallest people. Now, to find one person who belongs to this club, someone that doesn't have anyone who's taller than him, then you'll have to compare that person with all 30,000 people on campus. You have to compare that person, and if no one is taller than him, then you put him in this group, and now X is taller than anyone else on campus. But now, if you want to add more people to this group of the tallest people, assuming that the population did not change, so we are not getting new students, then to add person Y to this group, you don't have to compare person Y with 30,000 students or 30,000 people on campus. You just compare him with X. So if he's as tall as X, then you just add him to the group, because X has already been compared with everyone else. And then if you have person Z who claims that he is one of the tallest people on campus, then in order to accept person Z in the club, then you don't have to compare Z with everyone. You just compare him with both X and Y, or either X or Y. Either X or Y, because these people are all at the same level of height. They're all of the same height. So you don't have to compare Z with X and Y. You just compare Z with either X or Y. So it suffices to compare Z with only one of the people who are already in the club. And then if Z is there and you want to prove someone else like L, then you only need to compare L with one of these guys, not all of them. So this is exactly what happens with NP-completeness. So someone worked very hard to prove that this problem belongs to the group of NP-complete problems. But once this has been done, we can prove that a problem is NP-complete by comparing it with any of the problems that are known to be NP-complete. Not all, any of the problems that are known to be NP-complete. Now, given this, I can come up with an equivalent statement of condition number 2. The equivalent statement is, instead of for every problem L prime that belongs to NP, L prime is reducible to L, I can say for any problem L star that is that belongs to NP complete, that is already known to be NP complete, L star is polynomially reducible to L. Okay, so L star is polynomially reducible to L. So now you can prove that a problem is NP complete by either taking the hardest route, which is proving that every problem in NP is reducible to this problem, or you can take the easier approach, which is just you identify one of the problems that are already known to be NP complete and reduce it to this problem. And when you have multiple problems that are known to be NP complete, you have more options. Right. And among these options that are known to be NP complete, you only need to pick one of them. And if you can show that it's less than or equal to this problem in question in difficulty, then you have proven that L is NP complete. Of course, this will make more sense when we give some examples. So we will give multiple examples. Okay, but yeah. So now, if you have multiple problems that are known to be NP complete, how would you pick a problem to prove that a given problem is NP complete? Based on what? What do you think? Like you have some problem that I ask you to prove. Like I suppose that we don't know if you know that traveling salesman problem is NP complete and subset sum is NP complete, and you are trying to prove that the 0, 1 knapsack problem is NP-complete. Which one would you pick? Why subset sum? Yeah, so it's a good choice, but why? Because it's more similar to the problem that you are trying to prove. So you're trying to prove that this problem belongs to the club of NP-complete problems. So you find a problem in that club that is very similar. In fact, the more similar that problem is, the less work you will have to do in showing that this is reducible to that. So you will have to find an NP-complete problem that is as similar as possible or as close as possible to the problem that you are trying to prove. Okay? We will see examples. Now, before we move to examples, there is one more concept here, important concept. So now we are, today we are doing all the abstract stuff, but next time we will be showing the examples. But there are important concepts that we haven't introduced yet. Now, if a problem satisfies condition 2, but does not satisfy condition 1, then we call it NP-hard. So if a problem satisfies condition 2, but does not satisfy condition 1, then, or it's called NP-hard. So for example, the decision form of traveling salesman problem is NP-complete or NP-hard based on this. So the decision form of traveling salesman problem, is it NP-complete or NP-hard? Yeah, it's NP-complete because traveling salesman decision satisfies condition number 1. It is verifiable in polynomial time. Verifiable in polynomial time. So for example, TSP decision is NP-complete, and TSP optimization is NP-hard. Now back to that figure that shows the relations between P and NP. So you have P and NP. So here in P you have the easy problems like sorting and single source shortest paths and all of those problems that can be solved in polynomial time. In NP you have the hardest problem, which are the NP-complete problems like TSP decision. But TSP optimization does not belong to NP. So it belongs to NP-hard. So it's not here. Now the question is, what if someone discovers a polynomial time solution, a polynomial time algorithm for solving one NP-complete problem? What will the relation between P and NP look like? If someone comes up with a polynomial time algorithm for solving one NP-complete problem, what will the relation between P and NP look like?
Will they be same?
Yeah, they will be equal, because if someone can solve one NP-complete problem in polynomial time, all problems in NP are reducible to that problem, are polynomially reducible, so we can solve all of them in polynomial time. So here, if a polynomial time algorithm is discovered for one NP-complete problem, then the relation between P and NP will look like this. P equals NP. P equals NP. Now the point is that if such an algorithm exists, we don't know. So this is, so this is the P equals NP question. So this is an open question in computer science. We don't know if the relation is this or this. We don't know which one of these two relations is the right relation. Most people think that this is the right relation between P and NP. Most people think that here, we have some problems that are not polynomially solvable, or that P is a proper subset of NP. So most people think that P is a proper subset of NP, meaning, proper subset means that it's indeed a subset and there is at least one element that belongs to NP but does not belong to P. Or NP minus P is non-empty. So this is, P is a proper subset of NP. Okay? So this is an open question. Nobody knows the answer to this question. Most people think that this is the case, but nobody has been able to prove this. So now, in order to prove this, how would you prove this? For this, you have to prove that there is a problem that cannot be solved in polynomial time. So you have to find one NP-complete problem, and you have to prove an exponential lower bound on the solution time.